Gracias.
Buenos dias, and that's as much English, as much Spanish as I know. So I hope you all have your headsets and can follow along. So we'll be talking about faux encryption and the realities on secure storage on mobile devices. So the talk will be about different secure storage mechanisms on Android and iOS and what can go wrong along the way. I'm Daniel. I'm a security consultant with the NCC group. We are both from Chicago. And I'm more of an iOS person. I have developed a tool called IDB in the past, which is used for iOS pen tests. Maybe some of you have used that. And I give the talk together with Drew.
Yeah, and my name's Drew. It's glad to be back. I'm also a security consultant with the NCC group, as well as a research director for projects.
Cool. Yeah, NCC is a security consulting company. Probably you guys down here don't know us very much. We are headquartered in the UK, but we have a lot of offices in the US, and we do consulting, pen testing, testing of software, and things like that. So we give a brief introduction about the topic and why we think it's important to talk about it. And then we'll talk about iOS, which will be a bit more brief than the talk about Android, because Android is much more complex with all the different ecosystems and different OEMs involved and everything. So it will be a bit more on the Android side than on the iOS side, but we try to give you an overview on both of them. And then we try to give an outlook on what we see where there needs to be work done and what should be done in the future. So we all know that mobile devices are like the way most people use the internet almost these days, every day, everywhere. And if you look at this graph on the right side here, you see that most people are using apps on their mobile device. They don't use the browser and use the internet like we used to do. They all use apps. And what's different here is that traditionally, data was stored on the server somewhere in the cloud or in a data center, and we could enforce pretty strict access controls on who has access to that data. But now everything is downloaded to mobile devices and cached there and stored locally, so there is much more challenge in controlling that data on the device. So why is that a problem? Well, this is statistics for the United States, but there's a lot of phones which get lost or stolen within a year. And if you have data on the device and you carry it around everywhere, it's much easier to lose it and lose access to that data. But then, if you don't put anything on our phones, that wouldn't help us either, right? Because everybody loves our phones. We love to use the internet. We love to use apps and things like that. So we have a lot of data which is either has to be stored on the device or at least cached on the device. And if it's not data, then at least we need to have some sort of credential or access token or something which is stored on the device. So there is a challenge here on how do we make that work, and how do we make it work so that there is usability for the user is not a problem. If we make the user jump through a lot of hoops to get to the data, that's not working either. So we need to find a solution which kind of solves all these problems. And Drew will talk a bit more about the different nuances of that.
Yeah, so we all know there's no such thing as absolute security, but it's helpful to know like who you are concerned about in relation to the data on your device. So we have a couple different options here. The remote attacker, this is someone who connects to you remotely. A coffee shop attacker, somebody who breaks a crappy Wi-Fi setup or maybe takes over a Wi-Fi setup and attempts to take advantage of improperly secured applications and the communications of those on your phone. We have the casual thief who probably doesn't care at all about the data on your phone. They just want to steal the hardware and sell it to someone. More targeted attacks, this will be either a specific person or a group, and nation states who obviously have a lot more time, money, and power to do these kinds of things to you. So if we try to plot these on a graph of the sophistication and capability and the effort involved in that, we can kind of place these here. And as the security effort goes up, so does the defense effort needed to protect against these style of attacks. So I'm going to hand it back. Actually, no, I'm not. Just a quick word on full disk encryption. This is transparent to the user, so when a file is needed, it's transparently decrypted and read by the application in need. And when it's finished or new data is added, it's transparently encrypted when written to disk. Traditionally you hear that full disk encryption is only really going to protect you when the device is off. But that's also in combination with a strong passcode, because if I can guess 1234 or 0000, it doesn't really do you much good if the device is off anyway. So we need some more fine-grained control. And so now Daniel will tell you about what iOS offers in terms of that kind of control.
Thanks. So one advantage with iOS and Apple have over Android is that they control both hardware and software. So they can build hardware which supports software features, and they can build software which takes advantage of all the latest hardware they can put into the device. And that allows them to build security in pretty early in the process. And Drew will talk about the equivalent on the Android side. But for iOS, what we have is that the boot chain is completely signed. So from when the device starts booting, the bootloader is signed and checked. Then the bootloader checks the next step, and then that one checks the next step until you finally have the operating system all up and running. And all these signature checks are done in hardware so that you cannot inject any code or compromise the device during the boot up process. And then once the device is running and the operating system is there, all the updates which are installed are also signed. So you can't really install malicious updates and compromise them. At least you're not supposed to be able to do that. And also there's a feature which prevents you from downgrading, and probably a lot of us are annoyed by this because jailbreaks go away and things like this. But the reason is that if you have a security patch on your device, you can't go to a less secure version of the operating system. So they try to keep you secure. And then finally, if you have applications running on there, all these apps are signed, and the signing is actually on the code level. So even if you would be able to write data to the device and would try to run that, you couldn't, because you wouldn't have a proper signature on that code, and then the processor will just refuse to run that code. So but let's talk about data storage and encryption. So one of the problems with this is that if you want to store data on the device and you want to protect it, usually we use encryption for that. But if you just encrypt data, then you have the encryption key, and you need to do something with that. So if you need to store that somewhere. If you store it on the device, then we're back to where we started, just that we have a smaller piece of data to store. So what iOS does is that they don't store the key directly on the device. It's just deriving a key whenever you enter a passcode. It derives a key from that, and it uses that key to encrypt data. And that key can then be wiped from memory whenever you lock the device, and all that data cannot be read anymore. The problem with this is that users are particularly bad at choosing good at choosing weak passcodes and bad at choosing good passcodes. And obviously that comes back to what I mentioned earlier, that we want to be able to use our phones and not get locked out of them. So how to solve this? You can do brute force attacks easily now, but how do we solve this? One way of doing this is by using hardware. Even if you would compromise like the software, if you have something in hardware, you may not be able to get to that at all. And what iOS and iPhones and iPads do is that they have a hardware root of trust, the secure enclave, which is in the device, and it has a key which is tied to that chip on the device. So all crypto operations have to go through that chip. And even if you would copy data from the phone somewhere else and try to brute force the PIN code, you could not, because you're missing that piece which is only on the hardware. So that allows you to enforce controls in hardware, such as preventing brute forcing by just refusing to do anything else and just deleting the key, or to just simply wiping the device data if you have too many failed attempts. So this was a bit more simplistic. Let's look at how this works in more detail. So over here, this down here is supposed to be the data or file on the device. And on iOS, all files are encrypted. All data files are encrypted. And the file key is a specific key for each file. So every file has a different key. And that is used to encrypt the file. And that key is just stored with the file metadata on the file system. So that wouldn't help us much, because you could just read that file. So that's why the file key is encrypted with a file system key, which is actually tied to hardware key. The hardware key is what I talked about before, which is in hardware. That one is used to protect the file system key, and then all files are encrypted with that one. So this gives us the tying it to hardware and preventing attacks offline somewhere. But that doesn't help us if somebody steals the device, because they can just read all the data. In order to prevent that, we come to the passcode. So we have the passcode here, and we're using the password-based key derivation function to derive an encryption key, which is the key I mentioned earlier. And then this key is used together with this one to have a separate set of keys, and I will talk about those in a minute, just they're more complicated to what they can provide. And then those are used to encrypt the file key in addition to this one. So with this, we have something which is from hardware and something which is from the user. So if you don't have the user or you don't have the hardware, you can't really get to it. You may wonder, why do we have this key here at all? Well, the reason is that if you want to delete the data on the device, you can just, when you want to remote wipe your iPad, you can just delete that key, and then your data is not accessible anymore. So let's talk about the class keys here in the middle. So if you look at these, there are actually 3 different kinds. The first one is called NS File Protection None. The second one is NS File Protection Complete until first user authentication, and the last one is Complete. And what differentiates them is that the bottom 2 are tied to hardware and to the passcode, while the top one is only tied to the hardware. So this used to be the default for a while, and everything was tied to the device, but if you got the phone, you could decrypt everything you wanted. Then this one in the middle here protects your phone kind of like full disk encryption does. From the time your phone is off, when you turn it on, until you unlock it the very first time, till then it's encrypted, but once you unlock it once, the key will be kept in memory and will be able to read data all the time. And the last one is actually the stronger version. That one is being deleted from memory every time you lock the device. So once you lock the device, the key is gone, and then you have to type in the passcode again, and then the key is created again, and then you can access the data. So this is for files, and there's a very similar mechanism for the iOS keychain, which you probably heard of. Just some background on this. It's a store which allows you to store dictionaries of data or arrays of data or any kind of structured kind of data. And it's internally stored in a SQLite database on the file system. And it's not that the entire database is encrypted, but it's every entry in the database is encrypted separately, and that allows you to enforce different access controls. The main problem I have with this is actually probably a usability feature, but whenever you uninstall an app, it does not delete your keychain entries. So if you use an app 2 years ago and you uninstall it, and it had your username and password in the keychain, it's probably still in there right now. So if somebody can get access to that, maybe you sell your phone to somebody or you lend it to a friend, they can get to that data. So the protection is very similar. This is the column which is about files, which we just talked about a minute ago, and this one is the one for the keychain. And there is an equivalent for each one of these. I like that the keychain ones are named much more clearly. This data is always accessible. This one is accessible after first unlock. This one is when unlocked. And then there is a last one here, which is when passcode set. And the reason for that is if you are a software developer, like let's say you're a banking application, and you want to store something in the keychain, you don't know if the user has a passcode. So you may not be able to rely on that passcode protection. So what do? When long time there was no good solution for that on iOS, and since iOS 8 now, there is this flag when passcode set. So if you store data in the keychain with this flag, it will only get stored if there is a passcode on the device and not otherwise. So you may wonder, why do we need all these? Why don't we just always go for complete? So let's look at some built-in applications and what they are using, and maybe that gives some idea on why we need all of those. So there are some apps on your phone which just always need to get to their data. You always want to be able to get phone calls. You want to use your Bluetooth headset when your phone is locked. You want to maybe be in the VPN that you can get company email even when the device is locked. So all these apps just need to have access to the data even when the device is locked and you start it the first time. Then there's other ones here which can wait for a bit, like email, Wi-Fi, Facebook, things like that. You don't need them right away. You can turn on the phone, you can type in your passcode, and then you can use them. That's mostly fine for users. And then the last one, these are backups or Safari passwords. Nobody needs their Safari password when the device is locked, because you can't use the browser anyways. So there's the reason why there are many, and for you if you're a developer, you want to choose the one which best fits your needs there. So you all heard about the new trend to use your cat to unlock your phone. So these are Touch ID on iOS is more of a usability feature than it is a security feature. But the idea is that if you set up a Touch ID, you have to set a passcode. So everybody who sets up a Touch ID also has a passcode on their device. So it did a lot in the security that a lot of people didn't have passcodes before. Now they all want to use Apple Pay and things like that, so they have passcodes on the device. But internally, it's just used to protect the key, which we already talked about. That's why when the first time you start your phone, you have to type in the passcode, and then that passcode is protected by the Touch ID subsystem, which lives in the secure enclave, and only when you put your finger on there, it gets unlocked. And besides unlocking your device, there's two interesting features which you can use on an application level. The first one is tied to the keychain, and the idea here is that if you read the keychain item, at that point, you will have to put your finger on there or type in the passcode. And if you think about what we talked about, before we had no encryption, then we moved to, well, data is encrypted when the phone is off, data is encrypted when the device is locked, and now we're getting to a point where data is protected until you actually need it. So it's a bit closer to where you actually want to have access to the data, and you authenticate it at that point. And local authentication is another API which is out there. But that one is on the operating system level. It is not it's not tied to hardware or to crypto. So if you can root the phone by jailbreaking it, you can completely bypass this step, but you can't bypass that step. So this one is definitely the stronger mechanism in this. So since we talked about just jailbreaks a second ago, let's talk a bit what security threats are commonly left for iOS applications. So if you have a jailbroken phone, jailbreaks allow you to execute unsigned code on the device. So there is that it disables the code signing checks. And it also disables some OS level protections that you can maybe debug an application which you couldn't do before. But what it does not do is it doesn't disable sandboxing for App Store applications. If you have an app on your phone which is from the App Store, it is still contained and isolated just as it has been before. But if you install applications from Cydia or from one third-party source, and they will actually be stored on a different folder on the device, and they can do basically whatever they want. You can run them as root, and then they have access to a lot of data. But it will prevent you from getting to data. So if you have your device jailbroken and you give it to me, I may not be able to get to your keychain data because it is still encrypted under the passcode. So that protection doesn't go away just because you jailbreak the device. And also, most of the public jailbreaks cannot be performed if the device is locked. They always require you to unlock the device. I'm not saying that there is not people which have jailbreaks which work without unlocking the device, but the public ones don't work. So if your device is not jailbroken, what else do we have there? Well, you have malicious applications which are just asking for all the permissions, wanting all your photos, all your contacts, and shipping them off. Or you have apps attacking other applications using inter-process communication, like one app trying to exploit the URL handler of another app to get data which they're not supposed to. So there is that as a risk. And then lastly, there is evil mate-style attacks, which are maybe more for a jailbroken device, but it's more if I jailbreak your device. So maybe you don't have a passcode on your device, I steal it from you, I jailbreak it, and I backdoor either the operating system or I backdoor an app on the device, and then I can do whatever I like with that. So this kind of is what I still see as security threats on the iOS side. There may be more, but overall, they do a lot of useful things for developers, useful tools to build stronger applications. So Drew will now talk about how things look on the Android side and why things are more complicated there.
Thanks. All right, so let's look at how Android tackles some of these same problems. I put together this chart here of the sort of the evolution of security features and when they were added to the platform. And the ones highlighted in blue here pertain specifically to the topic at hand, secure storage. I've left the other ones in here as they are security protections, but not particular to storage themselves. Two of note here, the key store hidden keys I will talk about a little bit later. And this one is blocked, but it says force encrypt. And I will also talk about this one in more detail coming up. So if we look at the adoption of people using the newest versions of Android possible. I'm sure you've all heard of the fragmentation problem that Android has. We can see here that majority of people are still on a 2-year-old version of Android, KitKat 4.4. And Marshmallow, which admittedly came out about a week ago, is very little. But if we contrast that with iOS, which also iOS 9 came out very recently, there's a much bigger population that's using the latest and greatest version of the operating system. And so there's problems here that come from, Google may fix things, but you may not get that patch for quite a while, or ever on your mobile handset. So how does this impact application developers? This is a very complex problem because different protections are available in different versions of the platform. So this basically leads to a giant if-def mess where if you're trying to do things the proper way, you're going to check which version that the app is running in and then make different security decisions based on that. So this creates like a lot of code complexity, as you might imagine. And when we do application reviews, there's always like a massive section of like, if 4.2 this, if 4.3 do this. And so mistakes can be made a lot easier by developers in conditions like this because there's so many little esoteric problems that might arise from that. And as I said, access to more secure functionality is not really available to all users. So if you're running an older version, you may not have better protections. There's also the complicated problem of OTA updates, over-the-air updates that you might receive from your device. So Google may patch a problem tomorrow that is discovered today or reported, but it may be 6 months to a year before you actually see that update to your mobile device because there's 2 layers of middlemen in between you and that patch. The first one comes from the OEM themselves. So an OEM like Samsung heavily modifies Android's core frameworks and core operating system. All the crypto functions are much different. So they have to take Google's patch and apply all of their changes on top of that. And then once that happens, it gets passed to the carriers. And this may be particularly more of a problem in the United States, but carriers like to have their say on the builds. So they might want to add their apps to it. They may want to test it on their network for an extended period of time. And so all of this sort of adds up to like a very long time period before you might see a patch like that. I'm sure you've all heard stage fright in the news. This is a perfect example of thousands of phones probably abandoned for security updates because it's going to take so long for that to permeate out to your mobile handset here. So we'll talk a little bit about how Android encryption works. And it's based on DEncrypt, which is the block-based encryption of the Linux kernel's device mapper. They use AES in 128 CBC mode, and they use an ESSIV SHA-256 for each disk sector as an initialization vector. And as I mentioned before, this is transparent to the user. And there's 2 main keys involved in this process. The first is called the DEC, or the device encryption key. And this is what's actually used to encrypt the sectors of the device. And then there is a key encryption key, which sort of wraps that. And so the reason that happens is if you change your passcode, the entire encryption process does not have to repeat. You can just change the key encryption key, and the underlying device encryption key does not change. So this is much more from like a usability standpoint issue. So if we look at a visual of this, we can see the device encryption key I mentioned here, protecting the individual data here. And from here, we have the key encryption key and an IV that wraps this device encryption key. And then this sum is stored in what they call the encrypted DEC. And I'll get into more detail on this later. But this is stored in a partition on the device itself. But how do we get the key encryption key? So we derive that similarly to iOS from a key derivation function. From Jelly Bean and below for Android 4.3, PBKDF2 was used. Google decided to implement Scrypt in Android 4.4 to slow down brute force attacks and try to mitigate offline attacks on the passcode. And then in Lollipop, Google introduced an optional feature that allows you to wrap this key with hardware. So this key is bound to the device, and it also prevents offline attacks because now you need to perform the function on the phone. And as we know, phones don't have tons and tons of RAM and processing power like a cluster would to do this kind of breakage. So this introduces more security. Unfortunately, again, this is only available as of last year, and it's not very widely implemented at that. So we'll talk, as I alluded to, the encrypted deck here. So Android encryption only protects a single partition on the device, and that's known as the user data partition or /data. All the other file systems and images are not encrypted on the device. And so that encrypted deck I mentioned is stored in the crypto footer, which is most typically carved out of the very end of the user data partition as 16 kilobytes. More modern devices, there's a dedicated partition specifically for the crypto metadata. And as I mentioned, the master key is stored here as encrypted by the key encryption key, so the passcode, pin, or pattern that you've set on the device. If you're familiar with LUKS, it's kind of like LUKS, but not quite. One of the shortcomings is that the footer can only have one key slot, so you can only hold one decryption key. And so what a lot of people have done for the third-party Android market is allow you to have a much stronger boot password that's like a very long, complex password, and then have a second key slot for the actual passcode so that you don't have to type like an insanely complicated password every time you want to check your tweets or whatever you do on your phones. So the system credential store, similar to what Daniel was talking about, allows for the storage of VPN keys, Wi-Fi, asymmetrical keys. These are encrypted by the key encryption key that's derived from the user's passcode. And this can be hardware backed, and this is available on more and more models now. But what this means is that key material is stored in hardware and cannot be extracted by the operating system even as root. So it's much safer to store in here. Unfortunately, not every device has hardware backed crypto, and APIs are available for developers to check if that exists, and if it does, they can use that. But again, this sort of goes back to this code complexity of like, well, if they have it, let's use it. If not, okay, we're storing it, on software. Issues with the key store, though. Very inconsistent protections are available to developers. The key store was largely unusable, in my opinion, until Android 4.3 because it was just very weak. It didn't offer a lot of the protections that you might hope for, or features for that matter. It's very unclear in terms of the documentation on how keys are stored and when they're wiped. And actually, they fixed this in 5.0 because enough people submitted Google issues saying, my keys just randomly disappeared and I can't even reproduce the behavior. So this sort of results in developers not trusting the key store anymore, which creates a problem because they're going to try to roll their own solution and probably fail at doing so. However, this was fixed in 5.0, and it's actually much more improved with the latest release, Marshmallow. Unfortunately, some of your phones will never see Marshmallow until you buy a new one. So, but they've clearly defined the standards on what happens with this key behavior now. So it's a significant improvement, in my opinion. And if we look a little closer at the changes that Marshmallow brings, there's scrypt hashing of the unlocked passcode values. So once your passcode is, once you type it in, it's unlocked, it's stored. They've implemented scrypt to prevent attacks, and it replaces the weaker SHA-5 MD5, or SHA-1 MD5 hash concatenation that happens now. And the additional key store improvements I alluded to, they finally added support for symmetrical keys. So back on the evolution slide where I had stored the key store hidden keys, this has been possible for a while, but only available via private API. So it's not really something that you want to rely on in the past because it could just go away as it was not documented. So now this is officially supported and documented. And the behavior for when wipes happen, as I mentioned, is more clearly defined. And lastly, they provide additional properties for keys. So you can do things like prevent people from using fixed initialization vectors. You can prevent ECB mode, things like this. So keys have metadata now attached, and you can explicitly define what a key is supposed to be used for. And lastly, for Marshmallow, Nexus Imprint, similar to Touch ID in that a fingerprint scanner is now fully supported by the Android open source project. And this allows for better and more complex passwords, because now you can have a very long one to decrypt the disk at boot, and then very simply open the device without having to keep typing that in every time. So it encourages better usability for users, and I think in the end will produce more security as a result. And this is used very similar, secure payments for unlocking. This key material is stored securely in a trusted execution environment. So again, if you have root on the device, it should not be accessible. It's stored in hardware. And I think the most important thing that comes out of this is that Google's set a defined standard for how other OEMs are supposed to implement their fingerprint scanners. So up until this, I think really Samsung was the only major OEM that was including fingerprint scanners in their devices. So I think we'll have better standards for them to follow so that we have better security in the end. Speaking of OEMs, Google and their hardware partners have a very complex history. Android is very powerful in the sense that it can run on a very, very high-end device or a very cheap device. And so because of that, it's deployed everywhere on any kind of hardware that they can get it to build for. But unfortunately, that leads to a very complex situation in that you have no guarantees on what the phone ships with hardware-wise or what features it supports. And so we run into things like very inconsistent bootloader security. Some devices are very well locked down, and others will take anything you throw at it. We also, as I mentioned, may or may not have hardware-backed crypto storage. So again, weaker without. There may or may not be a trusted execution environment on the device, which weakens a lot of the security features that they've added recently. And even down to the boot image type, no one can agree on how to do this. So we have initial RAM disk boot images. We have init RAMFS kernels where things are baked into the kernel at compile time. We have U-boot, things that are just not standardized at all. And different OEMs offer very different protection schemes for these problems. So most notably, HTC implements eMMC write protection. So writes that to certain partitions are blocked at the storage level. So if you have root on your device and you try to overwrite a kernel, it will just discard the write because it's actually protected at that level. We have things like signature verification, which will come into play very shortly here. Some check the signature of the boot images, some do not. And then we have locked bootloaders, locked but unlockable, so like your Nexus or HTC programs or any of the other developer-friendly options that exist that allow you to enroll in this and then allow you to unlock the bootloader. And then we have, sadly, very permissive by default. And so this becomes a very difficult problem for Google to solve because they can't really force their OEM partners to do specific things as much as I think they would like to. And sort of back to what Daniel was saying, iOS has a very distinct advantage here because they control everything. So they can make their system much more cohesive and secure, in my opinion. So let me focus a little bit on the importance of boot security here. I've marked these as green and locked because these are reasonably safe. If you try to mess with a bootloader, you're going to break signature verifications as they hand off to each other. Probably going to break your device, and you need a lower level firmware tool to recover something like this. And assuming the user's elected to encrypt their user data partition, this is reasonably secure. But everything in here is open season. This is vulnerable without image verification. I can potentially overwrite the entire kernel on your device if I want to, and have root level execution. And similarly, the system partition, which is where the core of Android's operating system lives, is also not encrypted and thus vulnerable. Newer protections like DM Verity have been implemented, but again, this is coming from the kernel. So it's a problem where if I can replace this, then I've removed that protection entirely. So let's focus on a few practical implementations of vulnerabilities like this. So how many people have Samsung phones out there? Raise hands. Okay, fair number. So Samsung ships all their devices with a specific bootloader called download mode or Odin mode. And if you saw my talk last year, I focused a little bit on how you can use this. And so this is a very real application of something you can do with currently shipped devices. So internally, Samsung uses a tool called Odin to flash raw images to any partition on the device. You can interact and see all the different partitions, and you can arbitrarily overwrite them in a lot of cases. Unfortunately, Odin is a closed source Windows-only application, and it's also a very terrible piece of software. So a guy called Ben Doble from Australia created Heimdall, which is a cross-platform open source version that was just created by reverse engineering Odin. Sadly, this has not been kept up in a while, so later versions of Android, or specifically Samsung, have changed the way their bootloader works slightly such that this breaks, and you're going to have to do some hacking to get around that. Unfortunately, as you can see, this is ridiculously overly permissive. Like, no user should have the capability to do this on their device. And most devices allow direct write access. It will suck in anything you want to give it. There are a few notable US carrier protected models. Pretty much anything from Verizon for the last 3 years has had image verification, such that if you try to replace any bootable firmware, it just won't boot the device. It will still let you write it, but then you've sort of broken your ability to boot the phone. And we'll see a little bit more about that coming up. But I want to talk about some other weaker implementations here. So Little Kernel is a popular bootloader from Qualcomm. They have also had many issues, even though this is an open source bootloader. There's a lot of secret sauce that OEMs use and extend Little Kernel with, and unfortunately have been a few published CVEs detailing how this has not gone so well. This one, they just forgot to check if you were able to boot something. So you can boot an arbitrary image once in memory instead of writing it, but once you have a booted image with root, you can actually make changes so you can keep your persistent root. The next one is a little bit more complex, uses like a RSA kubroot attack, but you can forge signatures potentially and boot your own custom firmware that way. And this one is a little newer. When you flash a system image, it's usually a sparse bundle, but they didn't check the bounds of where that sparse bundle ended, so you can potentially overwrite past where you're supposed to go on the file system and make changes that way. And lastly, a newcomer, Laugh, which is properly titled because this is a hilarious backdoor on a lot of LG devices, including the Nexus 5, which really surprised me, which was fixed very recently. So this shipped on tons and tons of their phones in the last few years. It's a bootable partition named Laugh. It's similar to like a recovery mode that you can boot into. However, you can use the send command binary, which has been ported to other platforms via Python, and provide a single argument, which is the COM port the device is plugged into, and then you are rebooted into a root shell. And from there, you can overwrite firmware and do all sorts of things like that. So they realized, wow, this is probably a terrible idea. Let's try to fix it. Unfortunately, this did not work so well for them because they protected the partitions themselves. So partition 0p1 is protected, but they left block 0 unprotected. So with some DD and clever use of seek, you can find the exact partition you want to overwrite and still exploit this. So let's revisit the idea that full disk encryption protects your device when it's turned off. And we suggest that that's not always the case. So we want to introduce something we came up with called Rosie, the evil Android, evil maid. This exploits permissive bootloaders like ones we just talked about to flash a custom boot image. We've backdoored the kernel in this image, and in less than 2 minutes, including 2 reboots, we have a fully persistent backdoor on a device. You give the device back to the user and let them type in their decryption key. You can recover the encryption key itself. You can exfiltrate data from the device. You can get shells, anything you want to do. So I will let Daniel explain a little bit more about how we came up with this.
Cool. Thanks. Yeah, so sorry. This ties back into the things Drew just talked about, that there's no verification of the boot image whatsoever. So in this demo we will show you in a second, we first set up the device for our manual testing to just get it going. So we boot the device in the standard download mode, and then we use Odin, which Drew introduced, to flash a custom recovery on there. This one here is called TWRP, TWRP. And that one, then with that recovery on there, we can get a shell on the device and we can flash any partition with any data we would like. So what we then did, well, we wrote our own kernel module. I don't know if you can read this. So there's our backdoor kernel module, which we just download the open source kernel from the vendor because they have to provide those because of the licensing. So we download the kernel, and we added a custom module to it, which is just our backdoor, and then we compiled the kernel. And while we were developing this, it was basically the process was compiling the backdoor kernel, creating an image from that, flashing it, using the recovery, and then rebooting and testing. So that was just our development cycle. It's fairly easy. Probably if you look at Drew's talk from last year here at Ekoparty, he goes through how to do all those things in more detail. But once we have done that, we don't need to do this anymore. If we have everything ready, the attack is actually really quick. So we'll have a video here of the demo. Drew will talk about the first part.
All right, so here I'm showing the devices on. This is just so you can see that it works here. I'm going to turn it off because this attack is much more interesting when the device is off. And we'll see a shot clock counter sort of start in the bottom left-hand corner to count how long this actually takes. So here I'm booting into the permissive bootloader, and it says, custom operating system may weaken your security naturally, so I agree to that. And we connect the device, and you can see actually just how fast this runs. You'll see a green pass show up in the top left there. And there we go. The phone is fully backdoored in 23 seconds. So now the device will boot back up, and we will simulate giving this back to the user so that they can enter their decryption key.
Yeah, so the idea is that the user now, let's say you leave it at the table, you go to the bathroom, or you're going through airport security and they take your phone for a second, or anything you want to think of. So what we built is that whenever the device is unlocked, we will have a listener listening in the cloud somewhere, and we build a UDP client into the kernel, which will just read a file from the file system. And once the user unlocks it, it will just ship that file off to us. That was just as our proof of concept. We could have done anything else. It's going to take a few seconds until it gets there.
Yeah, I think we chose this example because we didn't really want to release like a weapon, I know, but you could do something and do anything you want.
And just for completeness, we're checking that we can open it, and then we go on the device to show you that we can read the file. So if we, as a regular user using ADB to go on the device, you can't read it. You'll see that in a second here. Probably hard to see. But it gives you a permission denied error. All right. So that's our demo. This is not specific to this device. We should probably add. It just depends on which device has these kind of boot level flaws, which we showed you. There have been multiple different ones along the way, and any future one which may have something similar would be vulnerable to such an attack until Marshmallow, which I think Drew will talk about in a second.
So Google added some protection, mandated their OEM partners force you to go into the developer options menu and allow OEM unlock, which now governs the control of this. So if you have the latest version of Marshmallow, this attack becomes a little harder because you have to get past the lock screen first.
And then I alluded to this earlier. The similar thing obviously works on iOS. If you can jailbreak the device, then you're at a similar thing. Just that jailbreaking a device with a passcode is very hard. But here we didn't even have to bypass the passcode because it's different. Right. Giving it back to Drew for a few thoughts.
So yeah, this is the slide called Drew's Soapbox here. I think there's a few approaches to how to fix problems like this, but the most important thing is these devices should ship securely by default. We want to see all of these things locked down in such a way that you cannot just get someone's phone and do this to them. But that doesn't mean just fully locking things and leaving it at that, because you're encouraging people to bypass these access controls because they legitimately want to customize their phone, or perhaps they need to pen test applications and need a deeper level of privilege for that sort of thing. So we want to see responsible bootloader unlock capabilities. Don't just leave us stranded with a locked device. Make us jump through the hoop to unlock it, agree to void the warranty, that sort of thing. We also want to see clearly documented security guarantees. It's impossible to know, unless you really research a specific model of an Android phone, what protections it offers you, what capabilities are provided there. And lastly, is consistency among OEM partners. I think that this is a problem that these companies can get together and agree on some standards on how to tackle these sort of things. So Daniel's going to talk really quickly about some alternatives to available platform security that exist.
Yeah, I'm going to keep it brief because we already talked about most of these things. What do you do if you cannot know that the user has a passcode set? Because we've seen that the passcode is such an important protection feature for both iOS and Android. Well, you can build a custom sandbox yourself. Just use the same techniques we talked about by deriving a passcode from deriving a key from a passcode the user types in every time you open the app, and then encrypt data with that and wipe the key. The big problem with this is, besides that crypto is really hard, it's really hard to get crypto right. The other one is, though, that you don't have hardware support, so you cannot prevent brute forcing very easily. Somebody can just copy your application data off the device and then brute force it offline, and if you have a 4-digit PIN, then that's really quick. So these things may not provide you the same protection as other systems. The other part is here, that may not work for all circumstances, but maybe you don't need to store all that data offline. Maybe you just pull it down when you need it and then delete it right after. If you need an application which has to have offline access, then that's obviously more problematic. Especially if you don't store a key or password on the device, then the user would need to log in each time, and that's a usability problem. So it's a lot of trade-offs and very difficult to do this without having operating system support. That's why we talk so much about what Android and iOS provide, because without that, it's hard. So where does this leave us? So for users and best practices, users definitely should set strong passwords on their devices because it's tied into such many security protections. And if you have iOS and Android, the latest versions with all the Touch ID and touch and fingerprint sensors, it makes it much easier to use this. If you're using iOS, you probably want to enable wipes after a certain number of password attempts, or at least remote wipes if you lose your phone, that you can delete it. And on Android?
On Android, I think we've seen that you need to choose your phone wisely. Unfortunately, this is something that you need to research and see what's possible with that particular model. But also, encrypt your device. Force encrypt, as I alluded to earlier, shipped with Lollipop, and then they took it back and said, no, it's still an electable feature. So this encryption is still opt-in, and we'd like to see this, forced on secure configurations. In general, as Daniel mentioned earlier, determine if the data actually needs to be stored on the device. This is obviously a complex problem, and every application has different scenarios where they may need to do this. But if you can get away with not storing data on the device, that's a good option. On Android, relying on platform security, as I've illustrated, is really challenging. You don't have all the guarantees that you should have available in all the different versions. And this is something we'd like to see more discussion on, is like, how old should your app support Android versions for? So do we want to just completely cut out certain versions of Android for your application to even run in because you just can't guarantee what protections exist there?
Yeah, and on the iOS side, choose something which protects your data with a passcode. I talked about those classes. And you can now warn the user if there's no passcode and tell them that the data will not be as secure if you're writing applications like that. So the road ahead is going to be very short because we already talked about those just as a summary slide here. For users, we have to find something beyond passwords because they're annoying and they're just not being used properly, and then people are at risk. Biometrics, Touch ID, and the new imprint one for Android are a good step there. And for developers, we definitely need more consistency in the platform, especially on the Android side, that they can do things right and are not confused by all the different options and the different wrong defaults which are documented there, which may leave them at risk.
So coming to an end here, the takeaways we hope that you got from this presentation are that security controls should be balanced with data security and the threat model. Decide how secure you need the data for your app to be based on who you're worried about attacking you. We'd like to see protected data until access is actually needed. So these things should remain encrypted until the second you need it, and then decrypt and then put back once you're done. And lastly, secure storage really relies on the entire stack being secured. I think as the demo illustrated, if any part of that chain is vulnerable, you've lost. So here's some references for you to read up more on some of these exploits and things that we talked about and researched. And thank you very much, everyone. Gracias to Ekoparty and everyone for watching.
¿Alguien quiere hacer alguna pregunta? ¿Tenemos tiempo para una pregunta? ¿Allá? Bueno. One question?
Sure.
Hi, thank you.
Hello.
How do they recover your password code when you return your Android phone, let's say to Samsung, and you lost your passcode?
So typically so you mean like if they want to refurbish and sell it to someone else or actually recover the passcode?
No, they say that if you forget your password and you can't recover it or you don't remember anymore, you can return your Samsung phone to the service and they will reset your password without losing your most of your data.
Yeah, I'm not entirely sure that that's possible if you've encrypted it with a passcode. I mean, they could potentially do something like we did to recover the passcode that way, but I think if you elect to encrypt your user data, there's really no way that they can do that.
This may be alluding to the passcode if you don't encrypt it, but you just protect your device with a passcode?
That's correct, yeah.
Because then you can do that, right?
Yeah, so if you have a lock screen passcode, but you didn't encrypt the file system, that is certainly possible. If you have elected to encrypt the user data partition, the key that protects that is not recoverable easily without some sort of vulnerability like that.
Yep. Sorry. Yeah. And there is really an advantage on those supposed secure phone like the black phone? And which is?
Yeah, so I like what Black Phone does in terms of they're very up to the minute on security updates. They take it very seriously, and whenever vulnerabilities are reported to them, they certainly respond quickly with patches. So that's a good behavior to see. I think unfortunately they're relying on Google's code as well. So any problems that exist in Android will potentially impact them as well if they haven't completely customized that portion of it. But yeah, I think things like that are a step in the right direction for sure.
From the point of view of low protection agency, is there any way that that software to make forensics analysis uses those exploits you're talking about?
I can't say with any guarantee, but I would assume very much so that agencies know and use things like this to their advantage.
Okay, and the second question, if I may
Sure.
ask, what do you think about 1+2?
So 1+2, I'm actually part of the CyanogenMod team, so I may be biased there, but I think it's good for the lower price models, and it gets quicker updates than even Google can put out because the CyanogenMod team merges changes in and they're available that night for the most part. So you can actually pull the latest things to your phone if you use the non-release build. So the community build, if you use the CyanogenMod that way, you can get up to the minute security updates.
I've seen also that it has like a fingerprinting device included. So how do you compare it's measured against iOS implementation or Apple's implementation?
So I actually don't have one, and I haven't looked at that specifically, but that's a good question. I think I'll follow up and figure out how that works, and because now I'm curious how they've implemented the security of that. So,
Thank you very much, guys.
gracias.